Well, let us come back to the discussion on solid oxide fuel cell. In the last class, we were discussing about specific advantages of the particular device. Just to continue with that, we have very high electrical efficiency up to 60%, particularly when the heat is also heat energy generated from the chemical reaction is also utilized. It is all solid state, that is again advantage. The other advantage is modularity. That is true of course for any kind of fuel cell, because a large capacity can be enhanced by adding few modules. So, there is a modularity. You do not need to have a very large capacity plant all the time. You can have few kilowatts to up to megawatts, whenever, depending on the necessity, one can add different modules and enhance the capacity. Multi-fuel capability is once again a very important advantage, particularly for the solid oxide fuel cell. It operates at a fairly high temperature. So, there is a hydrocarbons, particularly hydrocarbons can be used in this case, and large number of experiments have been carried out with natural gas, just the natural gas which contains different kind of hydrocarbons, and there is a in situ reforming, what they call, there is a in situ reforming at the anode side or the fuel side. So, the hydrocarbons gets on the spot or on site breakdown into hydrogen and carbon monoxide, and both of them can be used as a fuel in the system. And relatively low maintenance cost, because it is stable. All the components of the fuel cell are ceramic materials, and they are quite stable, their life is quite long. Of course, there is degradation, it is not that they do not degrade because of the different kind of interfacial reaction, because of some of the high temperature chemical reactions, but relatively their maintenance cost is low. So, these are some of the great advantages of solid oxide fuel cell, why a solid oxide fuel cell can be utilized for efficient power generation. However, as I mentioned, there are also certain disadvantages. High operating temperature is one hand advantage, but is also a disadvantage from the materials point of view. You cannot use all the different materials even if they have better properties, so far as the electrochemical activity is concerned. Cost of production sometimes is very high, although maintenance cost of the cell may be low because of the high long life, but cost of production, fabrication of ceramics requires high temperature, and being a brittle material, cost of production is always high. That is true for any ceramic material. Degradation of cell component at high temperature also is one of the problems. We will discuss that later on, because there is a chemical reaction, some of the aging behavior is that the structure gets changed because 2 or 3 different materials are in contact with each other and are maintained at a high temperature. So, there is always interdiffusion. It is very difficult to maintain a clean interface. So, that kind of degradation is there, difficult to make gas tight sealants. That is another very important problem, so far as the SOFC design and SOFC fabrication is concerned, fuel cell fabrication is concerned. We will look into that later on. Difficult to make gas tight sealants, particularly at a higher temperature. So, because we are talking about 2 different gases, so and we do not want that the 2 gases combine or come in contact with each other except in the desired way. Desired way is the electrochemical combustion, but otherwise they should not come in contact with each other, and therefore, we need to separate out the 2 compartments, and that is a very challenging task for any fuel cell developer. Well, with this let us come to what are the different materials we need for making a SOFC or fuel cell system. The major materials are three, we have already discussed. We need an electrolyte, we need a cathode material, we also need an anode material. These are the main three components, but in addition we also need another material like interconnect, and is called sealant. Okay. We are just discussing about the sealant. Sealant is a challenging task. Electrolyte, cathode and anode we have more or less discussed, their functions we have more or less discussed, we will discuss further. But what is interconnect? Interconnect is basically a material which connects the cathode of one cell to the anode of another cell. So, that is the purpose of, that is why it is called interconnect, because the overall EMF for each cell is within 1 volt, okay, within 1 volt, and therefore, if you are talking about a power system having several hundred volts or at least hundreds of volts and lot of sufficient amount of current has to be drawn, then a large number of cells are needed. Each cell generating less than 1 volt, a power pack or a stack needs a large number of cells. So, the cathode of one cell has to be connected to the another cell, and this is the purpose of interconnect. We will see how exactly the interconnect works in different designs. And sealant is an important issue of one of the designs, we will look into that exactly. And as I mentioned few minutes back, that the basic purpose of sealant is to separate the two compartments, the gas, make the whole system gas tight, and so that the fuel and the oxidant do not come in contact with each other except through the electrolyte. So, that is the purpose of the sealant, and since the whole system operates at a fairly high temperature, we need high temperature sealants and stable sealants. So, it is again a challenging task for any ceramic engineer or materials engineer. Well, these are the different kind of materials and some of the properties required for the construction of the solid oxide fuel cell. The kind of the electrolyte, these are the three headings: the electrolyte, cathode and the anode, and then what is the kind of physical form in which they are needed. Electrolyte must be a gas tight dense layer. Okay. The gas tight dense layer is the form in which electrolyte is needed. Now, one thing also is important here, what will be the thickness of the layer? Thickness has a very important bearing on the overall performance of the cell, because higher is the thickness, higher is the resistance, which gives rise to the higher internal impedance of the cell. So, one cannot draw a large current if one wants to. If the thickness is large, then the resistance is high and the current carrying capacity or the current density of the electrolyte or the system as a whole reduces. So, you cannot draw large currents. Therefore, there is always tendency to any design will have a very low thickness in the order of microns. So, it is not millimeter even, the electrolytes are in the order of few tens of microns. So, that is another requirement of the electrolyte, and it has to be completely dense. So, making a dense ceramics, as you can understand, is always a little challenging task. So, one needs non-porous material, whereas cathode and anode by design they have to be porous, otherwise the gases, both the reactants will not come in contact with the electrolyte, and so there will be no electrochemical reaction. So, therefore, they have to be porous, whereas the electrolyte has to be dense and it is thin, it has to be quite thin. Thermal property, because three of them are sandwiched together, the electrolyte, cathode and the anode forms basically a monolithic structure. So, their thermal expansion coefficients must match, otherwise there will be a crack and there will be bending, and the whole system will not be stable, because they are operating at a higher temperature. So, whenever there is a thermal cycling from room temperature to high temperature or high temperature to room temperature, there will be problem of cracking. So, one has to choose the material in such a way that there are many other criteria actually. For example, thermal expansion is one of them, but the materials must be chosen in such a way that there is no as such chemical reaction, high temperature chemical reaction between these materials which are in contact with each other. So, the electrolyte, the cathode and the anode, of course, the cathode and anode are not in contact with each other, they are separated by an electrolyte. So, the electrolyte and cathode and the electrolyte and the anode, they should not have any chemical reaction at the temperature of operation. There are many different alternatives available for the materials are concerned. Looking at these requirements, basic requirements, the electrolyte, of course, one of the major so far as the electrical property is concerned, right, I forgot to mention about that. The electrical property, what is the kind of electrical property requirement for these three materials? Electrolyte as definition, here is a fully ionic conductor, and in this case is an oxygen ion conductor. So, the conductivity is only through movement of oxygen ions, whereas cathode and the anode, cathode must be electronic conductor. There is no need of there should not be any oxygen ion conductivity here, but there will be sufficiently conducting at the temperature of operation. Whereas, in the mixed conductor, the anode must have a mixed conductivity, that means partly electronic, partly ionic. Okay, that is also another requirement for the anode. And in addition to, of course, you have a thermal expansion coefficient match with the electrolyte as well as the cathode. So far as the materials are concerned, these are the alternative materials available to us. Electrolyte, the most important electrolyte which has been used and is actually quite a stable material is 9 mole percent yttria stabilized zirconia, YSZ it is called. So, this is 9 mole percent yttria stabilized zirconia, it is a cubic fluoride structure. So, you have to stabilize the cubic fluoride structure so that you get sufficient amount of oxygen ion vacancy and fairly large fairly large ionic conductivity or oxygen ion conductivity. Some alternative materials are also there like gadolinium doped cerium oxide. Cerium oxide is also known to be a cubic fluoride structure, and adding gadolinium produces, in short, it is called GDC, and that also has a oxygen ion conductivity. It may also have some other properties, we will see later on. Scandium stabilized zirconia, SCSG, SZ, that is also used as can be used as a electrolyte, because it has a much higher conductivity compared to this one, but it is very costly and availability of scandium is also quite limited. So, there is some problem, otherwise in principle it can be used from the points of view with other properties. Strontium manganese doped lanthanum gallate. Lanthanum gallate is another compound which is supposed to have a very high oxygen ion conductivity, but its conductivity is quite high compared to YSZ or zirconia. Even at 100 degree, 150 degrees, you have the same kind of conductivity what you get with YSZ at around 900 degrees centigrade. So, the operation temperature can be lowered down to a large extent for lanthanum gallate, but for various reasons there is no compatible cathode or anode and their reactivity is little high. So, for practical systems people are working on these kind of materials, research is going on quite extensively on this kind of material, but no practical system has really come out, or a demonstration system has not really come out so far as the power packs are concerned. Cathode, there are a large number of possibilities. The most important cathode material is strontium manganite, sorry, lanthanum manganite doped with strontium. So, basically it is a lanthanum manganite LaMnO3, a kind of perovskite kind of distorted perovskite compound, and in which actually Mn is available in both 2 plus and 3 plus state, and that actually give rise to the electronic conductivity here. So, when you dope with strontium, it again gets stabilized in the high temperature form. There are couple of polymorphic forms, and it goes through a phase transformation somewhere around 600 degrees. So, if you want to, and the higher temperature phase is more electronically conducting than the lower temperature phase. So, if you want to stabilize the high temperature phase, you can dope with strontium, and the high temperature phase is get stabilized, and also the conductivity increases. In addition, there is another very great advantage is the thermal expansion coefficient of lanthanum manganese is not exactly same as that of YSZ, and so you have by doping with strontium thermal expansion can be matched with YSZ. So, that is the reason this is the most common, the most common and popular cathode material one uses for both for research and for development of prototypes. There are many other ferrite kind of compounds have been tried and being tried, like lanthanum doped cobalt ferrite LCF, lanthanum cobalt ferrite, it is I am sorry, these are repetition here, lanthanum strontium cobalt ferrite LSCF, and barium strontium cobalt ferrite BSCF. So, these are actually the different kind of ferrites also having a very good ionic electronic conductivity. These are all electronic conductors, not ionic conductors. So, all of them are good electronic conductors, primarily because you have a variable valency cations here. So, we have seen earlier that most of the oxides having variable valency cations will lead to electronic conductivity or kind of semiconductivity, and all of them have a good semiconductivity at higher temperature, and they are fairly stable at the operating temperature of the SOFC. So, these are some of the alternative materials or cathode materials one can use, and when it comes to anode, not many alternatives are there. The most important one of course is nickel YSZ. It is a Sarmet, it is a Sarmet in which nickel, metallic nickel is there, and YSZ is the same YSZ here. So, it is a mixture of the electrolyte material and metallic nickel, okay. Whereas it can be also used particularly with ceria doped electrolyte, one can also use nickel GDC, that means the Sarmet of nickel at GDC. So, normally the principle is you make a Sarmet, a composite of metal ceramic composite Sarmet of a nickel. Nickel is normally the common material used, which is stable at fairly stable at higher temperature and relatively less costly, and the electrolyte material. So, if you are using YSZ, one then make a Sarmet of nickel and YSZ. If somebody is using GDC, that is the gadolinium doped ceria as the electrolyte, the anode may be the Sarmet of nickel and the electrolyte material. So, these are the, this is the basic philosophy, and the philosophy behind it is it has to be a good electronic mixed conductor. In fact, this provides a ionic conductivity, this also provides ionic conductivity, and nickel provides the normal electronic conductivity. Okay. So, that is how it becomes a mixed conductor. But the more importantly, why we need a Sarmet? If we are talking about the electronic conductivity, then only nickel could have been used, but the problem is the nickel has a much higher thermal expansion coefficient. Nickel has a much higher thermal expansion coefficient because it is a metal, whereas this is ceramic. So, in general metals have much higher thermal conductivity, thermal expansion coefficient, thermal expansion coefficient than YSZ or any other ceramics. So, to match the thermal expansion coefficient and also to maintain the electronic conductivity between them within the material, one needs a SARMAT, a mixture of nickel and YSZ. That is how you match the expansion coefficient, thermal expansion coefficient with the electrolyte, because it is in contact with the electrolyte. So, we need electronic conductivity in the, so nickel or the metal provides that, and to reduce the thermal expansion coefficient, one mix the electrolyte also with that. But obviously, the nickel has a much higher thermal electrical conductivity than YSZ. So, the overall conductivity gets reduced. So, it is a one has to find out, make a compromise or optimize how much percentage of nickel and how much percentage of YSZ has to be used for this kind of SARMATs. We will discuss that little bit, how exactly what is the basic principle on which one decides or optimize the composition. So, these are the different materials one has for the combination of the three different materials of our interest. With this we come to another aspect of the solid oxide fuel cell, that is the design. The design is there are two major designs, there may be different other designs, but experimental designs, but these are designs which are more or less standardized. One is called the tubular design and this is called planar design. This is the basic difference. In a tubular design, you actually fabricate a kind of tube using the different materials of interest. So, this is a tube, basically you have a support tube which is a cathode tube. Air is basically a cathode. So, the support tube is a porous cathode, okay, maybe strontium dot lanthanum manganite. Okay. So, you make powders of that and then fabricate a porous tube. Over that one deposits a thin layer, the yellow ones basically, thin layer of electrolyte YZ, and then you have to have another anode on top of that. So, this red one is actually the anode. Okay. So, this is the electrolyte, the inner layer is the cathode layer or strontium dot lanthanum manganite, or in short it is called LSM, and the red one outside is the anode or zirconia, nickel zirconia SARMAT. So, that is how it has been made, and then the interconnect is here, the strip, the blue strip here is actually the interconnect. So, there is a strip which you can see it actually goes to the up to the cathode. So, there is a discontinuity of the electrolyte here and it goes directly up to the cathode and it is get exposed to the surface. So, this interconnect you will see how exactly it works. It actually connected here to the cathode, but the anode is separated out. So, it is not connected to the anode. So, there is a gap of the surface layer, top surface layer. Now, thickness is about this is about 2 to 3 millimeter in diameter, okay, 2 to 3 millimeter in thickness. The electrolyte is few microns, let us say about maximum is up to 50 microns, and in this case it is deposited by electrochemical vapor deposition. It is called electrochemical vapor deposition. One takes a volatile matter of the zirconium tetrachloride and yttrium tetrachloride, vapors are allowed to come from a chamber and then gets deposited on the surface of the porous cathode layer. So, there are a complicated process by which a completely dense electrolyte film can be deposited on this. So, this is your electrolyte, and over top of that one is to deposit the electrolyte, the anode, the zirconia anode. There are many techniques by which this can be done. One can do spraying or dip coating or plasma spraying. So, there are many different techniques by which one can do that. And this of course, once again it can be deposited by a screen printing or plasma spraying. Okay. So, these are the different techniques by which a tube like structure, basically a tube like structure is made, but this tube is not a monolithic tube, it is actually a sandwiched structure. The tube wall is actually a sandwich structure, and the tube wall acts as the MEA or membrane electrode assembly. So, you have the advantage over here is one can flow air because cathode is inside. So, the air can be flown through the inside of the tube, and the fuel can come in contact with the anode and it can flow outside. So, there is no question, it has become easier for the two compartments to be separated once you have a tubular structure. So, that is one way a solid oxide fuel cell, the whole tube acts as a cell, and the fuel is flowing on the outside and the air is flowing on the inside. So, this has been in fact was originally developed by Siemens Westinghouse, originally by Westinghouse and then Siemens Westinghouse, and several hundred kilowatts of power plants have been already demonstrated and prototypes have been built, and they have been operated at different countries, particularly in Japan with natural gas and so on. Up to 50 to 60,000 hours of continuous operation has been demonstrated by this tubular fuel cells. There is another design which is called the planar design, and once again in a planar design, well, it is a very simple thing, it is just a sandwich structure the way we have seen it earlier. Instead of a tubular structure, we have just a planar structure, and we will see later on there are various kind of designs once again within the planar structure, whether it is electrolyte supported or anode supported or cathode supported. Okay. So, these are some kind of a indicative figure. So, far as the thicknesses is concerned, the electrolyte here you can see about 200 microns, which is about 0.2 millimeter, the anode is 50 millimeter, cathode is another 50 micron, and cathode is another 50 micron. This is what we call the anode supported one, this is electrolyte supported. Okay. You can see because 50 micron cannot be self supported, 50 micron cathode or 50 micron anode cannot be self supported, the mechanical strength is not good enough. So, you need another thicker material, and in this case it becomes electrolyte. That is what the original design was, electrolyte supported, but later on more efficient design have come up. These are anode supported, what we call the anode is much thicker here, where the electrolyte is much thinner, and that is about around 10 micron. Well, 10 micron is quite thin, but normally it is about 20 to 30 micron is quite natural or quite regular. Cathode once again is about 50 micron. So, these are just sandwich structure, planar structure, but the problem here is you have to separate out the fuel side or the oxidant side and the fuel side. So, one needs a other kind of support structures or the sealed chambers, so that the two gases can flow and do not come in contact with each other. So, that is a challenge, of course, we will see how it can be done. Well, this is the expanded view of the supported structure, the tubular structure. This is the cross section of the tube, which we have already discussed, right. This is the anode, the white one here is the cathode, and then there is a additional layer, what they call cathode functional layer. Well, we will come to that later on, what is the cathode functional layer, because in between the electrolyte and the cathode one produces or gives another very small layer or thin layer of a different material, which is advantageous from the point of view of drawing larger currents or higher current density. So, this is the cross sectional view of the tubular cross. This is the overall another view of the tubular structure. It is little more exploded view, but it is basically the same. Okay. This is the assembly. This is the assembly by which the tubes are finally put together. This one can have stacks, so that you can see this is the cross section of the tubes again, and these are this is the interconnect. So, the cathode is connected to the outside of the next cell. So, the outside is anode here and the inside is cathode. So, this is how the interconnect works. Okay. On this side, of course, this is a parallel connection. This is a basically they are nickel felt. Okay. A nickel mesh is used to connect anode to anode. So, sidewise they are connected anode to anode, and vertically they are connected cathode to anode. So, this is a series circuit and this is a parallel circuit. So, the battery of large number of such tubes can be put together, and finally one can have a cathode bus here and the cathode anode bus here. So, there is a positive charge, the anode are connected parallelly and the cathodes are connected parallelly. So, by that process you can have a battery of systems, a battery of cells, individual cells or battery of tubes, basically a large number of tubes stacked together, so that a power system can be fabricated. These are the different designs so far as the planar designs are concerned. One can say this is an interconnect. Okay. Before that, this is your electrolyte, this is electrolyte supported, anode supported and cathode supported. The basic difference is the dimensions of the three layers. Here the electrolyte is much thicker, the white portion is the electrolyte, here the this is anode supported. So, this white is actually anode, and this thin layer of the white layer is actually the electrolyte, and the other one is the cathode. Okay. So, here it is cathode supported. So, just the reverse of that, the cathode, this is cathode, a thicker area is cathode, once again a very thin layer is the electrolyte, and on top of that the anode is there. Okay. So, the dimensions are given here, the cathode is about 50 micron here, the electrolyte is more than 150 micron, earlier we have seen about more than 200 micron. So, it varies between 150 to 200 micron, electrolyte is less than 20 micron here, whereas anode is much larger, anode is almost 0.5 to 1.5 millimeter in thickness. Here cathode is about 300 micron to 1 millimeter, and electrolyte is still less than 20 micron, anode is top layer is all the time 50 micron. So, whether it is anode, whether it is cathode, and here is also the cathode. So, that is how this is the structure, this is the sandwich structure of one single cell. This similarly, this is the design of the anode supported, this is cathode supported. The current trend of course is primarily the anode supported one. Okay. So, the anode is again porous, right. Now, interconnect here is in a different form. This is one interconnect. In fact, because of the thin electrolyte used here, the operating temperature has come down. You can also notice the operating temperature here is higher because the electrolyte thickness is higher. So, to reduce the internal resistance, you have to heat it to higher temperature. So, the operating temperature 800 to 1000 degree centigrade. By reducing the thickness of the electrolyte, one can reduce the operating temperature to 600 to 800 degree centigrade. So, the anode supported, both anode supported and cathode supported, where electrolyte is much thinner, is about 20 micron in thickness, the operating temperature can come down. So, this is one advantage of this. Now, interconnect here is in a different form. Interconnect is, there is one interconnect here, there is another interconnect there. So, there are two interconnects, and in the interconnect you have some channels. These white spots, white groups are actually basically there are some groups, and once it is in contact with the plane surface of the anode, it actually forms the channels. So, these are the channels through which the fuel gas is allowed to pass through, whereas on the other side the channels are used for the this is the anode supporter. So, the cathode, so the oxygen or air is allowed to pass. So, these square hot the white spots or the white square cross section pot are actually the channels through which the gases are passing. So, on one side you have a this is the anode one. So, it is fuel and this is oxygen. If this is cathode, then this becomes oxygen and the other side becomes fuel. So, the interconnect here in fact in a different form. So, if you can stack, this is only single layer, if you can stack large number of layers one after the other, then the cathode side will be coming in contact with the anode side. So, on the other side also there will be some channels like that. So, these are plates actually, these are metallic plates in this case, because the operating temperature has come down to 600 to 800 degree centigrade. So, some of the metals can be used, which is not possible when this the temperature operation is a little high. In these cases there is no metal which can withstand more than 800 degree centigrade. But if the temperature of operation is between 600 to 800, there are some metals, particularly ferritic steel, the high chromium steel can be used and being used these days. Okay. So, this is, so the construction is different and one has to seal these part of the area, okay, so that the gas is allowed only through the channels, either this channel or that channel, and the gas does not come out outside. So, there will be some sealant, there will be some glass sealant has to be used to seal the interconnect with the either with the anode or with the cathode. Okay. So, this is the different designs for the planar structures. This again the expanded view of the similar structures. Only thing we have some material here, this is an anode supported one, this is the anode where 1 to 2 millimeter and 30 to 35% porosity, coarse pores are there. Okay. And then you have the white region is actually the electrolyte 20 micron thick, and the density is about 98% fully dense. These are the cathode films, once again about 30 to 40 to 50 micron in thickness, and the porosity is up to 30 to 35%, coarse pores is called. Then there are two additional layers. The three layers are normally the standard layers, but we have additional layers. One can say cathode, it is called whichever is in contact with the cathode and the electrolyte, or in between the cathode and the electrolyte, this layer is called the cathode functional layer. That layer is called, it is very thin, it is about 10 to 15 micron, again porous, but these are finer pores. Okay. These are finer pores than the original cathode. Here also you have another material which is called anode functional layer, okay, and the material I am just coming to that, and compared to this anode which is a coarse pore, okay, this has a finer pore. So, there is a gradient of pores in fact. One is the material is slightly different. Here you can see the cathode side is LSM YSZ, that means a mixture of the basic cathode which is LSM, pure LSM, and a mixture of something like your Sarmet, what we have used in nickel YSZ. Instead of nickel YSZ, we are basically using here LSM YSZ, that is a mixture of the cathodic material and the YSZ which is the electrolyte, and the pores are much finer. So, we have basically, if you go through across these two layers, the initially we have a coarse layer, and then in contact with the electrolyte there is a finer layer. Same thing happens here on the other side. The anode, basic anode has a coarse pore, and then the cathode anode functional layer which is NiO YSZ. Okay. This is in fact it is not NiO, one can have NiO because it is, this is Ni, and this is NiO YSZ, which of course under the reducing condition will finally go to Ni. So, NiO is not that stable in presence of hydrogen. So, NiO will get reduced to Ni. So, finally, it becomes an Ni YSZ, just like the composition of the original anode material, but more importantly it is a finer pore size. So, it has once again a gradient of pore size, coarser pore to the finer pore. Now, advantage of this is to increase the current density. I mentioned earlier that we need a contact or what we call a triple phase boundary, that means a contact between the electrolyte, the anode and the gas phase. These two must come in contact as much as possible. So, which is possible, which is the contact area may be enhanced by reducing the pore size. So, finer is the pore, this contact area or triple phase boundary area gets enhanced, and so the number of reaction sites, number of the interfacial reaction site increases, and therefore, you can have a higher current density, you can draw more current, more gas can pass through and more current can go through or pass through the circuit. Same thing happens in the other side also. If you have a finer pore size in contact with the electrolyte, the triple phase boundary, area of the triple phase boundary increases. So, you have a more reaction sites. So, the exchange reaction takes place much in a large number or large amount or large extent, and then you get a higher current density. However, you cannot have all through these finer pores. If you have a very fine pore all through, then there is a problem of gas diffusion. So, the overall diffusion rate will reduce. So, that will restrict the movement of the gas, and therefore, one can have one would not have enough reaction sites. Reaction sites will be there, but the gases will not be available, and therefore, the current density will reduce. So, it is always better to have a gradient of pores, finer pores towards the electrolyte side and coarser pores away from the electrolyte side. Same thing happens with both in the cathode as well as in the anode side. So, that is the reason one uses a 5-layer model instead of a 3-layer model. One can use a 5-layer model and with a gradient of porosity, and as well as sometimes these materials are different. Here of course, just a mixture of the normal cathode and the electrolyte has been used, or a normal anode and the electrolyte has been used, but some different materials can also be used to enhance the electrode kinetics. So, this is another way of designing. This has been shown in a different view, but this is the isometric view, and this is the interconnect. this is the interconnect. So, there are two interconnects and one can see this is the anode, the green one is the anode and the black one is the cathode, yellow one is the electrolyte. So, there are two anodes have been shown. This is the continuation, this is the start of the next layer, next unit cell, okay, the next single cell. So, this is single cell. So, these are the groups, and normally the groups, as you can see, there are groups on either side of the interconnect. So, this is one gas. So, this is in contact with the cathode. So, this is oxygen side, and below this is the anode side. So, this is fuel. So, on either side of the in fact it is connecting the anode from on one cell to the cathode from the other cell. This is an conducting material, and metal is certainly a good conductor. So, or alloy actually, ferritic steel. So, that is a good conductor. So, it provides the electrical contact and also provides the channels for the flow of reactants or the gaseous reactants, and there is a cross flow. This is a cross flow design. So, the flow of fuel is in perpendicular direction to the flow of oxygen. So, oxygen is flowing in this direction, or air is flowing in this direction, and the fuel is going along this direction. So, this is the stack, it is a kind of stack design, one after other one can stack a large number of such cells, then they can be connected parallelly outside. Well, this is another thing, in fact, how these cells are finally designed or fabricated. These are tape cast sheets, flexible tape cast sheets, large number of flexible tape cast sheets are actually compressed together. This is the anode, this is the anode material in the form of tape, and then only one tape of zirconia, stabilized zirconia. So, single layer of electrolyte is there, and then a few number depending on the thickness of the each individual tape, as well as what will be the final thickness of the support tube, support anode. So, these are nickel YSZ, tapes which has been pressed together in the cold condition. So, by putting a load you actually compress them, and this is the multiple layers of anode nickel. In fact, one other thing need to be mentioned here. To start with, these compositions are basically nickel oxide and YSZ. Okay. So, we form the nickel oxide YSZ, and then during its use, when hydrogen is passing is allowed to come in contact with this at a high temperature, the nickel oxide gets reduced to nickel. So, finally, the stable form is nickel YSZ sarmet. Okay. So, by taking few numbers of the tapes, actually you can control the thickness, since you need about 1.1 to 1.5. So, several layers of such things can be compacted together in the cold condition, and only one layer is put for the electrolyte or the only pure YSZ, and then there can be co-sintered, that means sintered simultaneously, so that the nickel YSZ gets sintered on the surface of this anode. So, that is how one actually makes. So, the flexible nickel YSZ tapes as cast, layer thickness is about 300 microns, so several of them, and then fabrication tape casting plus lamination, we call the lamination. So, anode supported thin film electrolyte is actually one of the techniques. It is not the only technique by which it can be fabricated, but this is only one of the techniques by which the tapes can be formed. So, single tape casting machine can be used for the same purpose. These are some of the examples of typical examples of cells made at CGCRI in fact. So, these are the tapes made at CGCRI at some point of time while I was there. These are basically nickel OSZ anode. This is the basic structure, nickel OSZ anode, and then this black one is actually screen printed LSM. Okay. The screen printed LSM is here. So, the typical dimensions are there, it is 50 by 50, 50, these are 4 inches by 4 inches I believe, no, these are 2 inches by 2 inches, 1.5 millimeter. Later of course, the same group is also making 4 inches by 4 inches cells. So, the electrolyte thickness is about 40 microns in this case, and cathode is about 50 micron, and this is about 1.5 millimeter. So, of course, there are the challenges of fabrication is there are tremendous amount of challenge, because you are sandwiching 3 things together, and particularly the electrolyte, making a dense electrolyte on a porous substrate is always a very difficult job, and one has to find out whether there are pinholes and so on, that has to be avoided. So, this is certainly a challenging fabrication technology. This is a typical microstructure, the cross section, and one can see this LSCF layer. There are actually 4 layer here. The anode functional layer is not there. These are the anodes. This whole thing is porous anode. This is the electrolyte, is about 20 micron in this case. Okay. These are the electrolyte, dense electrolyte layer, and then there is a LSCF, one of the cathodic material, which is a finer pores. You can see this layer is finer, and then much larger pores. Okay. So, this is LSCF cathode. Cathode is not LSM, it is LSCF, it is there, and then CGO as the interlayer functional layer. Okay. The CGO has been about 10 micron, this is 20 micron, this is 10 micron, and this is about 15 micron, this is about 1.5 millimeter. So, this is a typical cross section, and as you can see, to make a dense material within the porous material by a co-firing technique is always a difficult job. So, this is typical cross section of a planar SOFC membrane electrolyte electrode assembly. Oh, this we have seen, and what is happening? Why? These are the typical current voltage versus current curves, current density curves. You can draw different amount of currents at different voltages. So, these are the these are the voltages across the single cells, of course, these are all single cells. So, as you increase the current density, load is increased, more and more current get drawn, and the voltage comes down. So, normally at 0.7%, 7 volt, whatever the current density we get. So, if there is a open circuit voltage, when low, the current is low, voltage is high obviously, and as more and more current is drawn, the voltage comes down. Okay. So, this is the thickness, this is a kind of thickness dependence. You can see the YSZ film is here about 35 micron. So, you get a current density of 1.2 ampere per centimeter square, and overall wattage about 0.7 per centimeter square, whereas if you have a lower thickness of the electrolyte in the same structure, you have a higher current density 1.55 ampere per centimeter square, and 0.9 watt per centimeter square is the total wattage of the single cells, of course. Okay. These are once again the data presented from the CGCRI group. Well, I think I will not discuss it this time. We have some more interesting features need to be discussed, but that can be discussed in the next class. For the time being, let me stop here, and whatever remaining maybe we will discuss in the next class. Okay. So, thank you for your attention.